Hello and welcome back to Deeksha Karnataka YouTube channel, and in Masterstroke today I am going to discuss two chapters together, atoms and nuclei. So both chapters are not super heavy, not super difficult, but when you are studying two chapters at once you might feel, sir, this will be too much. Actually not. These two chapters are mostly fact based and some information based chapter, not too much of calculations and not too much of understanding is there, okay, except few of them you might require. In nuclei chapter, atoms chapter, many of the old concepts are now deleted, so only few of them are there. So we will start with the chapter. First we will start with the chapter atom, and we will see what all we are going to discuss in this chapter, right? So first of all we will start with beginning of atomic physics, then Rutherford's experiment, atomic spectra, Bohr's atomic model, energy levels, and de Broglie's explanation of Bohr's atomic model. So these are the main things of this chapter, and let us start with the beginning of atomic physics. So Dalton's atomic theory is the first theory that dealt with how matter behaves, okay? So Dalton was the first. He says that if you start breaking matter into smaller and smaller particles, you have to stop somewhere where basically this is the smallest indivisible particle. You cannot divide it anymore, and that was Dalton's atomic theory. And that theory was accepted widely because of the lot of things associated with it. Most of the observations during that point of time are actually obeying Dalton's atomic theory, and that's why we also started studying Dalton's atomic theory when we were kids, okay, because that point of time whatever Dalton did was actually that much the information that is available was not very high. Okay, nowadays it's when we are kids we studied Dalton's atomic theory. Now let us move on to the next part where something brilliant happened, that Dalton said that atom is indivisible. So people never look beyond that whether you can divide it further or not, but somehow during some experiment J.J. Thomson discovered negatively charged electron. So it was understood that where from this electron is coming from. So he termed this electron was named by J.J. Thomson, and he termed that negatively charged particle with whose mass by charge is known. And he said that basically this electron is actually coming from the atom itself. So atom, which was considered to be indivisible solid particle, actually it is turned out to be, it is not super indivisible. You can divide atom further and you can extract some negative particles called electrons from it. Okay, then it was whenever some new discovery comes into our mind, we always say that then what is the structure of this, how it is being embedded or how it is located inside the atom. So that is the first question that people asked, and it was said that the atom is solid still, like Dalton, because Dalton gave the solid theory, atom is solid. So still the physicist back then said the atom is solid, and electrons are like cashews or plum inside a pudding. Okay, pudding is like a cake. Okay, and plum is like raisins, nuts, dry fruits inside that cake. Some of you may have eaten Christmas cakes or fruit cakes. Okay, fruit cakes are basically where you have all the dry fruits inside the fruit cake. So basically you can say that is the fruit cake model, okay, where fruits, dry fruits, cashews, raisins embedded inside a fruit cake. Okay, so those are like electrons, the fruits are electrons, and the cake itself is a positively charged atom itself. Okay, so the cake itself is atom, and the fruits are like electrons which are positioning itself inside the fruit cake randomly, right? So that was the first plum and pudding model. But when some model is given, there is one more requirement. So first you discover something through some experiment, then you go back to your theory, you try to correct the theory, and then again you go back to the experiment and try to prove that your theory is correct. Okay, so electron, previously it was understood that atom is indivisible, but it was found that atom can be divided into some particles. And so when this discovery happened, then they said how it is located inside the atom. Then J.J. Thomson itself gave the plum pudding model, and he said they are embedded like plums inside a pudding. Okay, then Rutherford came into the picture. Rutherford was a student of Thomson, and he said, okay, let us verify whether my teacher's model is correct or not. So what he did some experimentation, and after that experimentation he found something. We will discuss that. But what we are seeing here, condensed matter and dense gases at all temperatures emit continuous distribution of electromagnetic radiation. This radiation, due to oscillations of atoms and molecules, governed by the interaction of each atom or molecule with its neighbors. So these are all observations, and these observations actually was not super clear from the palm pudding model. How you are observing certain emission of wavelength, okay, which is basically due to the vibration of atom, but still it is not clear. Okay, so that's why Rutherford started to decided that because the observation and the theory is not matching, let me prove the atomic model itself. Okay, if I can show some proofs of the atomic model directly, then it will be proven that okay, the atomic model of the Thomson's atomic model or palm pudding model is correct or it is not. Okay, so in there is a idiom that says "Doodh ka doodh, pani ka pani." So something similar happened over here. So let's check whether how much milk is there, how much water is there. Okay, so what he did, he took a very thin gold foil. Okay, Rutherford's gold foil experiment, okay, or gold leaf experiment, you might say. So what he did, he took a very thin layer of gold. Why he chose gold? Because gold is very malleable. Malleable means you can make a very thin layer out of this metal. Okay, not all the metal supports it. That's why if you see sweets on top of some of the costliest sweets, they have a gold, very thin layer of gold on top of it. Okay, gold foil. Why it is so? Because gold can be made in very thin layer. Okay, if you take that gold, it will not be even 10 rupees, but you can make it a you can make things appear beautiful by making a very thin layer of gold. And that practice was very ancient. During ancient times also, even without the knowledge of metallurgy and electrons and protons, human realized that gold can be made into a thin, very thin layer. Okay, that is how the practice came into existence. So he took one such foil, he hang it using some mechanism. And basically what does it mean? That one single layer of gold consists of only one atom in it. Okay, so this is basically, you can say that if you take a solid metal, okay, solid metal, if you take say, if you take a solid metal, okay, there will be multiple atoms present. Okay, multiple atoms. Okay, multiple atoms will be present like this. But when you take gold foil, so here are multiple atoms present like this, but if you take only single gold foil, it is very thin, so each position only one atom is present. Okay, so anytime if you are interacting with this, you are interacting with only one single atom, not multiple atoms. So that is very important, because if you want to test the theory, you have to take only one single layer of atom, not multiple layers of atoms. Okay, so what he did, he took this gold foil and he took a source of alpha particle. Okay, what is alpha particle? Alpha particle is basically doubly positive helium ion. It is a doubly positive helium ion. Its charge is 2e. Okay, 2e plus, that is positive, and its mass is 4 times mass of proton. Okay, now so what sample he used? He used bismuth 83214. Okay, so that is the name of the sample that he used during his experiment. Okay, so he took this sample over here, he allowed the alpha particle to pass through this gold foil. So what this experiment resembles, let me give you one idea. Suppose you have a wall. Okay, you want to check whether the wall is solid or not. So for that, what you do, you take a bowling machine. You have seen all bowling machine from where the balls are being bowled and the players practice cricket, or baseballers practice baseball, or tennis players practice tennis. So that is called bowling machine, through which automatically a ball is being delivered at certain speed. So you can consider this as the bowling machine, natural bowling machine. Okay, so there is a complete reserve of balls. The balls are helium particles, so those basically hitting this gold foil. So what you are doing, you have a solid wall in front of you, and you have a bowling machine, and you allowed the bowling machine to throw the balls towards the wall. What will happen? You will see that because the wall is solid, okay, you will see that most of the balls are actually coming back. Maybe one or two can pass through. There are maybe, if there are some holes, or there may be one window present or one door present, okay, or there is an exhaust hole present. Through that, maybe one or two ball can pass through the other side, and based on the angle, some can go in this angle, can this angle, but most of the balls you are expecting to come back because the wall is solid. Right, correct. So what initially when Rutherford started his experiment, he was expecting that most of the alpha particle will come back because it's a solid layer of wall. But when he did his experiment, he was astonished to find that 99.9% electrons actually went straight ahead without much deflection. Okay, so 5.5 mmB alpha particles emitted from bismuth to 83214 source, radioactive source, at the thin metal of foil made up of gold of thickness 2.7 into 10 to the power of -7 meter, just like a gold foil. The scattered alpha particles were observed through a rotatable detector. So this is the detector, okay, and screen and a microscope. The scattered alpha particles on striking the screen produced a brief light flashes of scintillation. So when this alpha particles is hitting the screen, you will see some light flashes that will give an idea, okay, where these alpha particles are hitting the screen. Okay, so because alpha particle is radioactive, the source is radioactive, alpha particles, high energy alpha particle can be harmful for you. So human presence should be less in this experiment, and that's why the experiment was designed like this way. Okay. Now, the observation is very, very interesting. As I mentioned, many of the alpha particles pass through the foil. It means that they do not suffer any collisions. Okay, so if you see, this is the graph, this is the number of new particles deflected, and this is the angle of deflection. Okay, so if you see that most number of alpha particles pass through them without any deviation. So the same experiment, imagine in your head, you are throwing a ball through a solid wall, but the ball, instead of coming back, they are passing through the wall. Okay, that means the wall is not actually solid, it's mostly hollow. Okay, so that was the expectation from the experiment, that most of them will come back, but instead of most of them coming back, most of them are passing away, right? So they are actually going through the gold foil, which is very, very interesting. Only about 0.14%, so as I mentioned, 99.9% they are passing without any deflection. Only about 0.14% of the incident alpha particles scattered by more than 1 degree. Okay, so 99.86% electrons passed directly. Okay, so approximately 99.86% they scattered directly, and only 0.14 scattered more than 1 degree. Okay, 1 degree, you know, that is in your degree scale. Take the 1 degree, you can understand the meaning of 1 degree. So that many electron alpha particles scattered only 1 degree. In about 1 in 8,000, 1 in 8,000 deflected by more than 90 degrees. So 1 in 8,000, that is a very, very low percentage, and that one alpha particle came back. 1 in 8,000, more than 90 degree means it deflected back, not straight away but some other angle, it deflected more than 90 degrees. Okay, Rutherford argued that to deflect the alpha particle backwards, it must experience a large repulsive force. Alpha particles are positive in nature, so if the entire solid surface was positively charged, then it would have, all of them should have been coming back, but most of them are passing away and only few are coming back. 1 in 8,000, coming back. That means those cases, they are experiencing some huge repulsive force, and because of that repulsive force, alpha particles are coming back. Okay, so the repulsive force could be produced if the greater part of the mass of the atom and its positive charge were concentrated tightly at its center. So that is the structure of atom that Rutherford gave. Okay, Rutherford said entire mass of the atom and all the positive charges together, they are sitting at the center and electrons are orbiting around it. Okay, that is the basic model of Rutherford. Now let's see one question based on the concept that we have studied. A beam of fast moving alpha particles were directed towards a thin film of gold. So this is a thin film of gold, and we are allowing multiple alpha particles towards it. The parts A, B and C of the transmitted and reflected beams corresponding to the incident parts A, B and C are to be shown. Okay, in the adjoining diagram, the number of alpha particles in A dash will be minimum and B dash will be maximum, C dash will be maximum. So let us understand. So here A, B and C, three incident beams are falling on this. Okay, B dash is exactly reflecting back, A dash is passing through the gold foil, and C is passing with an angle more than 1 degree in this direction. So what we have learned so far, that 99.86 of them actually passing straight, 0.14% is deflecting by more than 1 degree, and 1 in 8,000, which is almost insignificant, but still you cannot ignore that 1 as well. That 1 in 8,000, that is coming back. So this is the largest. A dash is largest and B dash is the A dash is largest, B dash is smallest, C dash is somewhere in between. Let's see the answer. Okay, A dash will be minimum, no, A dash is maximum, C dash will be minimum, C dash is still not minimum, B dash will be minimum and C dash is maximum, no, not correct. A dash will be maximum and B dash will be minimum. So A dash is maximum, B dash is minimum, so option D is correct. So whenever you answer such question, read the options carefully, understand the question, then you will be able to answer any question coming from these two chapters. Now before I want to continue with this discussion, just want to tell you that if you want to learn how to solve difficult questions in an exam situation, then KCET 30 days batch is online and it is available for purchase. Okay, here you will get 30 days live online crash course. Also you will get all the KCET previous year questions. You will get complete syllabus revisions for PU1 and PU2. You will get chapter wise KCET PYQ in test format. You will get 10 full length KCET mock tests. Okay, and here you will get the batch starts from 21st of March 2026. So but you might think that, sir, this is after PU2, but currently there is a special price available for this crash course, which is 2499, and the offer price is available till 25th of February. Till 25th of February this offer price is available. After the 25th of February the price might increase. After the board exam price might increase. So don't wait, register yourself. The link of how to join the batch is given in the description section of this video. Click on that link and join KCET 30 crash course batch today to secure a good rank in your KCET exam. Right, now let's continue with the discussion. Rutherford's experiment observations. The incoming alpha particles could get very close to the positive charge without penetrating it, and such a close encounter would result in a large deflection. So if the alpha particle, when they are traveling into the atom, when they are coming very close to the positively charged center of the atom, we are calling it at center. Okay, when the alpha particle comes very close to the center, it deflects by a huge amount, and that is why this is called close encounter. Okay, this agreement supported by the hypothesis of nuclear atom. So this is where the hypothesis of nuclear atom comes, where it is said that all the positive charges are located at a center which is called nucleus, and all the other electrons and all the other particles rotating around the nucleus, like the sun and our planets. Okay, so solar system where sun is at the center or nucleus, all the planets are rotating around the sun. Similarly, here we are considering that the nucleus is basically the center of the universe, and all the electrons are orbiting around the nucleus. Okay. Now this agreement supports the hypothesis of the nuclear atom. This is why Rutherford is credited with the discovery of the nucleus. So who discovered nucleus? Rutherford, Ernest Rutherford. Okay, Ernest Rutherford is the person who discovered the nucleus. Okay. The magnitude of the repulsive force can be calculated using this formula. Okay, 1 by 4 pi epsilon naught, Coulomb's formula. This is nothing but Coulomb's law, Q1 Q2 by R square, as simple as that. Now, impact parameter and distance of closest approach. These are very, very important concepts. The trajectory traced by an alpha particle depends on the impact parameter B of collision. The impact parameter is the perpendicular distance of the initial velocity vector of the alpha particle from the center of the nucleus. Suppose here we have the nucleus, and alpha particle is coming from this. This is the source, and this is the alpha particle which is coming to hit this nucleus. Obviously it will not hit. So if you trace this path, and if you measure the distance between the nucleus and the alpha particle trajectory, then this is the impact parameter B. Okay, this is the impact parameter B, and if the impact parameter is small, then it interacting with the nucleus more and more, right? So closer it is to the nucleus, better chance of it being deflected, right? So that means when the impact parameter is 0, if B equals to 0, then it is actually going straight towards the nucleus, but it will not be able to hit the nucleus. Before reaching the nucleus, the repulsive force will push it away. Okay, the impact parameter is the perpendicular distance of the initial velocity vector and the center of the nucleus. A given beam of alpha particle has a distribution of impact parameters B, so that the beam is scattered in various directions with different probabilities. Okay, probability and statistics you have learned. It is seen that an alpha particle close to the nucleus, small impact parameter, suffers a large scattering. In case of head-on collision, the impact parameter is minimum and alpha particle is rebounded back. Okay, this is not a particle, this is alpha particle. Okay, for a large impact parameter, the alpha particle goes nearly undefeated and has a small deflection. Okay, so if the impact parameter is small, deflection is more. If impact parameter is large, deflection is small. Okay, inversely proportional. Distance of closest approach. Okay, when the alpha particle is heading straight towards the nucleus, when the alpha particle is headed straight towards the nucleus, before it is repelled back by the nucleus, the distance between the alpha particle and the nucleus is called distance of closest approach. So this is the allowed distance till which the alpha particle is allowed to go. Okay, through the scattering process, the total mechanical energy of the system consisting of an alpha particle and a gold nucleus is conserved. The energy is conserved. Initial energy is kinetic energy, so obviously the alpha particle consists of entirely kinetic energy. Its final energy is electric potential energy when the alpha particle momentarily stops. So alpha particle before reaching the nucleus, so this is our nucleus. Okay, before reaching the nucleus, it's momentarily stop over here before coming back. Right at this point, its entire energy is potential energy. When it started, its entire energy was kinetic energy. So that means if the energy is conserved at this distance of closest approach, entire kinetic energy should be equal to electrostatic potential energy. So what is the formula for electrostatic potential energy? K Q1 Q2 by D, and kinetic energy is half mv square. So based on velocity and distance, we can say that the distance of closest approach is inversely proportional to square of the velocity. This formula is important for your KCET exam because or MCQ question in your board exam as well. Okay, so distance of closest approach is inversely proportional to square of the velocity. Now there are very few mathematics left in this chapter. This is one of them. Now atomic spectra. Let us discuss atomic spectra. Each electron has a characteristic spectrum of radiation. When an atomic, so not electron, sorry, each element. So for example, if you observe hydrogen, okay, you will observe certain light being emitted by hydrogen. If you take say helium, you will get a different light from coming out of helium. Each element, if you now you might say, sir, if I take iron is a solid, how it can emit light? So you have to take vapor of that element. Okay, basically in gaseous state all elements emit light. Okay, if you take vapor, sodium vapor lamp is one of the oldest lamp used in practice. Okay, sodium vapor lamp is basically yellow light. Helium lamp is one of the blue light. Okay, halogen lamp, when you mix multiple different element, you get a white light. Okay, so different gases give different colors of light. Okay, based on that we say neon light. Neon light means different gases give different colors of light, and based on that different signage and symbols are designed, and that's why it is called neon light. Nowadays LED is there. LED has replaced most of the other forms of light, but still if you go back few years, you will still see that many colorful lights are actually made of original glass. Okay, so when atomic gas or vapor is excited at low pressure, usually by passing an electric current through it, the emitted radiation has a spectrum which contains certain specific wavelengths only. For example, as I mentioned, sodium vapor lamp produces only yellow light, whereas helium produces only blue light. Okay, so if you allow current to pass through helium tube, it will show you violet to blue light. If you allow sodium vapor chamber, and if you allow some current to pass through it, it will give you yellow light. So that is the characteristic spectrum of those elements. Okay, helium or sodium. The characteristic spectrum of hydrogen atom is given below. So this is the characteristic spectrum of hydrogen. You will see some of the lights. Some of the lights are in visible region. Some of the lights are in outside our visible region as well. So all elements do have some lights in visible. Some of them are in invisible range as well. Invisible means ultraviolet or infrared. Now this thing was actually not been able to explain by Rutherford. There was one more other problem of the Rutherford's atomic model, is that Rutherford says that positively charged nucleus and electrons are orbiting around it. Okay, now electrons, so positively charged nucleus will have an electric field of its own, right? Positive charge means it will have outside electric field, and when an electron is moving in a electric field, okay, it will experience a force, and because of this it will do some work, and because of that it will slowly lose its energy, because we say that when a charge is moving in an electric field, a charge is accelerating in an electric field, it will give rise to electromagnetic radiation, right? Accelerated charge gives rise to electromagnetic radiation, and as it is radiating electromagnetic radiation, it will slowly lose its energy, and it will slowly, its radius will decrease, and it will jump into the nucleus. So the atom, when it is created, it will destroy after a time of 10 to the power of -8 seconds. So atoms are created and immediately they are destroyed. So that means you, me, your mobile phone, your exam pattern, nothing is existing here, right? That would have been greater, no? Right. So basically Rutherford's atomic model fails miserably to describe the stability of atom and describe the atomic spectra. Mainly hydrogen spectra we will discuss. So everything, okay, the structure was perfect. The alpha particle scattering experiment can be explained. Okay, positively charged nucleus can be explained. Electrons are orbiting can be explained, but it will not be able to explain the stability of atom, it will not be able to explain the characteristic spectrum of atom as well. So that's why now, so J.J. Thomson's student was Rutherford. Now Rutherford's student was Niels Bohr. So Niels Bohr, now he came up with a theory, okay, and he did not perform any experiment. He just taken up the result of Rutherford's experiment and he came up with the theory so that he can explain how the electrons and positively charged nucleus are still together inside the atom. So that's why he came up with three postulates. Postulates are like laws, okay, which cannot be broken, okay, which seems not super common in our day-to-day life, but it has to be obeyed by everyone. That's why it is called postulates, okay. So postulate means they are true, they are always true. It is not like something you can find a flaw in them. It will always be true. That's why it is called postulates, and we do not need any experimental proof for this. So postulate means something which is considered to be true, and for that we do not need any experimental proof. No direct experimental proof is required. That's why they are called postulates. So what are the Bohr's postulates? He said that an electron in an atom could revolve in certain stable orbits without the emission of radiant energy, contrary to the predictions of electromagnetic theory. So he first came and he said, no, electrons, even though they are accelerating, even though they are moving in the presence of positively charged nucleus, the electron will not emit radiation when they are in a particular orbit. So Rutherford did not specify any specific orbit. He said electrons can orbit anywhere. That was the fault of Rutherford. But when his student Niels Bohr came, he said no, electron cannot radiate anywhere. They have a specific path. For example, if I say that you want to go from here to point A to point B, you have to take the road through that point only, right? Either you take road or you take train. So if there is a direct train connection, you can go from point A to point B, but if there is no direct train connection, you have to take other transport as well. But if the path travels through some jungle, for example, Bannerghatta jungle is very close to this place. So you cannot cross Bannerghatta Zoo without taking the road. Okay, you cannot go through the jungle itself. Okay, so you have to take the road. You cannot go through the jungle. So Rutherford's way was through the jungle. Niels Bohr's way is through the road. He says that okay, there is a fixed road. Electron can move only in those roads. It cannot cross that road and go into the jungle. Okay, if he wants to go somewhere else, he has to follow the roads only. So it has to go. It has to move in the fixed roads. You cannot move into the jungle on your own. Then there will be a tiger who will come out and eat you. Just for joking. Okay. The electrons around the nucleus only in those orbits for which the angular momentum is some integer multiple of h by 2 pi. Okay, where h is Planck's constant, thus the angular momentum of orbiting electron is quantized, and that angular momentum is given by nh by 2 pi. Okay, in future though, if you study physics, you will learn that nh cut. This is called reduced Planck constant. H by 2 pi occurs too many times in physics, in especially quantum physics. So this is the reduced Planck's constant, where h cross is h by 2 pi. Okay, so we do not like to write something too many times. In your class you are writing it only once in this chapter, so h by nh by 2 pi is okay. Where n equals to 1 is called ground state. Okay, that is the level, the minimum energy required for the electron. An electron might make a transition for one of its specified non-radiating orbits to another of the lower energy. When it does so, a photon is emitted having energy equal to the energy difference between the initial and final states. The frequency of the emitted photon is given by h nu equals to ei minus ef. Suppose this is the higher energy orbit, ground state, and this is the lower energy state orbit, higher energy state, lower energy state. This is the ground state, this is a lower energy state or excited state. Okay, Now when the electron gains sufficient energy, it will move only from here to here. Okay, electron cannot jump somewhere middle and start rotating there. Electron will only can jump from this state to this state, and when they are in this state, okay, and if they want to decide that they want to come back to the ground state, then they have to radiate some electromagnetic radiation. And if this is say E1, this is E2, and the energy of radiation is given by E2 minus E1. Okay, this is the difference in energy. Okay, one mistake over here. This is slightly tricky because here it is E1 minus E2, initial minus final. So that is one thing. Remember, bigger minus smaller always. Now let's move on to Bohr's atomic model. Radius of boron, and there are few facts that you need to remember. Radius of nth Bohr orbit is directly proportional to square of the orbital or number of the orbit. So n is quantum number of the orbit. So quantum number, if suppose 1 is ground state, 2 is first excited state, 3 is second excited state. So radius of the electron orbiting in a particular orbit is proportional to square of the quantum number. Energy of an electron in nth Bohr orbit is given by minus 13.6 by n square. This is valid for hydrogen. Okay, this is valid for only hydrogen. Frequency of electron orbiting the nth orbit is inversely proportional to 1 by n cube, and time period is proportional to n cube. So these are only the concept that you require to solve some numerical questions. Okay, let's see one question. The ratio of area of first excited state to the ground state of orbit of hydrogen atom is. So what is the area of first excited state? Area of first excited state is n equals to 2. Okay, n equals to 2 gives the first excited state. So A2 will be pi r2 square. Right, area means pi r square because they are all circular orbit. So this is plus. So electrons are orbiting like this. So this is ground state, n equals to 1. This is first excited state, n equals to 2. So area means pi r square, formula of a circle. Okay, what is n equals to 1? Ground state, A1 is given by pi r1 square. Okay, now what? Now the ratio of A2 by A1 will be simply r2 square by r1 square. Right, now r2 square is actually 2 whole square into some constant, and r1 square is 1 square into the same constant, because radius is proportional to n square. Radius is proportional to n square. So now k cancels obviously, and you get 4. So the ratio is 4:1. Okay, so first excited state to the ground state is 4:1. Now de Broglie came into the picture, as I mentioned in the last chapter. The de Broglie was a student of humanities. He was studying history, but later on he came into physics after learning about the discovery of Einstein, and he also came to help Niels Bohr when he studied about this atomic theory of his. So de Broglie said that these are the fixed orbits where electrons moving in its wave form, electrons moving in its wave form, not in its matter form. Electrons are present inside the nucleus in its wave form, and these orbits are those where electrons can form static waves. Static wave means two waves coming from opposite side. If two electrons moving in a same orbit, if they are moving in the opposite side, they will interfere with each other and they will form a static wave. Static wave means nodes and nodes, they will match, antinodes, node, node, antinode, and after the circle they will match the same point. So node and node. So if they are not matching some antinode and from one side antinode, one side node, that orbit is not possible. So electrons basically, when they are in this particular configuration, it will not emit any radiation, and he even calculated the angular momentum. He even calculated the angular momentum of the electron, which is nh by 2 pi. Okay, so this was a question in your last year's model question paper, that de Broglie's explanation of Bohr's explanation, Bohr's second postulate. Okay, so de Broglie proposed that electrons exhibit wave-like properties and their motion in the orbit can be described as standing wave or static wave. For an electron moving in an nth circular orbit of radius Rn, the total distance is the circumference of the orbit 2 pi Rn, and thus the wavelength can be given as 2 pi Rn equals to n lambda. N is the quantum number. Okay, and from there he has established that mbn Rn equals to nh by 2 pi. Okay, so this is the explanation of de Broglie. De Broglie explained the Bohr's hypothesis. Okay, both are theoretical discussions, and later on with the observations we see that Bohr's model is also not correct. So Bohr's model also has some limitations. The Bohr's model is applicable to hydrogenic atoms only. So even though Bohr was incorrect, it is actually it is correct only for one atom, hydrogen. That means something what Rutherford and J.J. Thomson did wrong, Bohr did something correct. So this is actually the basic of modern atomic theory. Okay, all the atomic theory that you study in chemistry, they all started from the previous, obviously from Dalton, but Bohr was the someone who actually took some correct steps, and he was the first to show us the way, and from there entire modern atomic theory evolved. Okay, so it cannot be extended even to even more than 2 electron systems. While Bohr model is correctly predicts the frequencies of light emitted by hydrogen atoms, the model is unable to explain the relative intensities. So some of the lights are strong, some of them are weak, so that cannot be explained using Bohr's atomic model. Okay, now one more point was there, that it cannot explain some of the splitting of atomic spectra, Zeeman effect, Stark effect. Those are some of the other limitations of Bohr's model. If you study physics in future, atomic physics, you will learn more about Bohr's atomic model. Now let's continue with the last chapter, nuclei. Nuclei is most theory based, so we will just go through the concepts one by one. So first of all, experiments on scattering of alpha particles demonstrated that the radius of nucleus was smaller than the radius of an atom, okay, by a factor about 10 to the power of 4. So that means if the atom is this big, nucleus is very, very small. Okay, so the radius of nucleus and radius of atom differs by a factor of 10 to the power of 4. That means 10,000 times. So nucleus is 10,000 times smaller than that of the entire atom. This means that volume of nucleus is about 10 to the power of minus 12 times smaller than the volume of the atom. Okay, so radius is 10 to the power of 4 times smaller. That means volume wise or size wise, okay, nucleus is 10 to the power of minus 12 times smaller than that of the atom, considering that atom is spherical. Okay, so in other words, the most part of the atom is empty. If an atom is enlarged to the size of a classroom, the nucleus would be the size of a pinhead. The pin that you put on your notice board, the head of the pin. So that is the size of the nucleus if you consider your entire classroom to be the atom. Okay, so nucleus is very, very small. Okay, and why nucleus is important, by the way, because later on we discovered protons, and we realized that protons all are sitting together inside the nucleus, and it is almost impossible for the nucleus to be stable because Coulomb's repulsive force is enormous, huge. So some force has to balance that Coulomb's force, and that's why we discovered more stronger force than Coulomb force, that is nuclear force. Okay, now let us discuss, we will come to that in a while. First start with atomic mass of the atom. Okay, so mass of an atom is very, very small, thus we needed a new unit to express the atomic masses. This unit is the atomic mass unit, represented by the symbol small u. defined as 1/12 of the mass of the carbon atom. You learned about this in chemistry, so I am not doing too much detail about it, but you have to remember that one atomic mass unit is approximately 1.66 into 10 to the power of minus 27 kg. This value is not important. If you need to use this value, that will be provided in the question, but the other value, that is 1 U equals to 931.5 MeV per c square, is very, very important. And some cases, based on the question, we can approximate this to be 930 as well for competitive examinations. Only for competitive examination you can approximate that to 930. If you are using the value in your board exam, then 931.5 exact value you have to use. Mass defect related questions. Now, composition of nucleus. So the positive charge in the nucleus is that of the protons. Okay, so later on Chadwick discovered protons, and neutrons was also discovered. So proton carried 1 unit of fundamental charge, that is 1 E. Okay, neutrons are neutral but not stable. So protons are stable. Neutrons, which are neutral in nature, are not stable in general. A neutron decays into a proton and an electron and an anti-neutrino. So stable means if you leave a proton alone, it will remain proton. If you leave a neutron alone, it will no longer remain as neutron. It will decay, or it will split into a proton, an electron and a anti-neutrino. Anti-neutrino part is not there in your physics syllabus. It is a particle which actually helps to maintain the rotational angular momentum. But if you are interested, you can do some research on your computer. I will not go into the detail of anti-neutrino. Nucleus does not contain electron. Inside the nucleus, by the way, there is no electrons. Neutron can decay into proton and electron, but there is no free electron or independent electron present inside the nucleus. Nucleus is free of electrons, only protons and neutrons. The composition of nucleus can now be described by using the following terms and symbols. Z is atomic number, number of protons, N is neutron number, number of neutrons, A is mass number, Z plus N. Okay, symbol of a nucleus, particular element nucleus, is given by AZX. Okay, A is mass number, Z is atomic number, X is the symbol. Okay, for example, 19779 AU, gold. Okay, it has been found that the nucleus of mass number A has a radius R equals to R0 A to the power of 1/3. Okay, R0 is 1.2 femtometer or 1.2 Fermi. This is the radius of any nucleus. Based on this mass number, you can calculate the radius. Okay. A nucleus at rest splits into two nuclear parts having radii of the ratio 1:2. Their velocities are in the ratio. So a nucleus initially was rest. Now it breaks into two parts. Their radii is, this is 1, this is 2. Okay, the velocities are in the ratio. What is this, sir? There is nothing is given. How to do that? So this is like a collision problem where you have a bomb. The bomb splits into two masses. Okay, what is the ratio of their velocities? So in that case, mass is given. In this particular case, mass is not given, but the radius is given. Okay, so radius is given means bigger the radius, larger will be the mass. Okay, now how mass and radius is dependent on it. So suppose the mass of this is m. Okay, mass is say m2, so this is m1. Okay, now mass is proportional to its mass number. Mass is proportional to its mass number, right? More number of nucleons means more amount of mass in it. And we also know that the radius is proportional to its mass number to the power of 1/3. So it is proportional to mass number of 1/3. Similarly, R1 will also be A1 to the power 1/3. Okay, now this is 1, this is 2. So we can take the constant, or you can find the ratio directly. Now we know that because initially it was at rest, initially completely its momentum was 0, mv was 0. So finally its momentum is m1 v1, and that should be equals to m2 v2. If this is moving in this direction, this will move in the opposite direction. Okay, so m1 v1 should be equals to m2 v2, and we are trying to find the radius of ratio of velocities. So that is basically m2 by m1. Okay, so what is a1? a1 will be r1 cube, and a2 will be r2 cube. Okay, so mass is directly proportional to mass number, and mass number is proportional to cube of the radius. So we can write this as r2 cube by r1 cube. So basically only thing you need to remember, mass is proportional to cube of the radius. So it will be 2 cube by 1, so that is v1 is to v2 will be 8 is to 1. So correct answer is 8 is to 1. Clear? So this is just a formulation, but if you remember that mass is proportional to cube of radius, you can solve this question quickly without much thought. Now if you want to practice more such questions and absolutely free of cost, then we are bringing you a free KCET PCMB mock test paper, and it is available to download from our Vedantu website. What you have to do, you have to click on this link given in the description section of this video, free KCET PCMB mock test PDF download. Click on that and register with your mobile number, get the OTP, put on the OTP, and you will be able to download the PDF for absolutely free. Okay, and you can keep that PDF, you can use that PDF multiple times, you can solve it. If you have any doubt, you can ask us during our live doubt session as well. So this PDF is available for absolutely free of cost. So if you want to practice more questions for physics, chemistry and maths, and if you want to see how the question paper looks like before your KCET exam starts, then you can download this question paper absolutely free without paying any charge. Right? So the link given in the description. What are you waiting for? Go and download now. So Einstein's famous equation E is equal to mc square. Here is the energy equivalent of mass m is related by above equation, and c is the velocity of light, vacuum, and approximately 3 point. We all know that. Okay, E is equal to mc square. We are learning for a so long time. So why this formula is important? Let's check that. We have seen that the nucleus is made up of neutrons and protons. Therefore, it may be expected that the mass of nucleus is equal to the total mass of its individual protons and neutrons. So, you went to a market, you buy 1 kg apple, you buy 1 kg orange. Okay, so if you have a bag in your hand, if you put 1 kg apple, 1 kg orange, and if you measure that bag, weight of that bag, what you are expected? You are expected to get 2 kg, right? So you can imagine that apple is actually the protons, oranges are the neutrons. So if the total mass of orange, total mass of proton is 1 kg, total mass of neutron is 1 kg, when you are adding them up, you should get 2 kgs. I am just increasing the value. Obviously 2 kg is too much for the mass of a nucleus, but I imagine that. Okay, so you are supposed to get 2 kg of both of them. But when you combine these two and if you check the weight, you will see that the weight is not 2 kg, it is 1.8 kg. So you rush back to the shopkeeper saying that you must have mistreated me, you have cheated me, you have taken something out. Then the shopkeeper taken everything out and they measures, and he found no, see, 1 kg, but when you are putting them together, the weight becomes 1.8 kg. Now that is not possible in your normal supermarket purchase or normal purchase from the market, but that is possible inside a nucleus. Very, very interesting part. Okay, so however, the nuclear mass m is found to be always less than this. So individually the masses are more. When they are put together inside the nucleus, the mass is always less. This difference of mass is called mass defect. So nature is actually cheating by reducing the mass. Okay, so nature is the cheater. He gives some mass into it. Okay, actually it is not cheating, it is helping us. Because of that we all are all the universe is possible. Okay, so what is the mass defect? Mass defect is given by total mass of the nucleons, that is number of protons into protons, mass of protons, number of neutrons into mass of the neutron, minus the given mass. Based on this formula, there used to be a problem on your PU board exam, but this year I don't think that this formula based problem will come, but you should practice them anyway. If you want to break the nucleons into its constituent protons and neutrons, extra energy half a delta mc square must be supplied. So this is the part of Einstein. Okay, so if you want to break the nucleus, the energy associated with this mass defect, you have to provide it to the nucleus. Okay, so you have to bribe it, take this amount and be separated. Okay, must be supplied. This energy required is related to the mass defect by EB equals to delta mc square, Einstein's relation. Now this is called binding energy. This energy binds the nucleus together. Okay, and binding energy per nucleon, that is the binding energy per each proton or neutron, total number of neutrons, total number of nucleons is given by EB divided by atomic mass. Okay, so EB divided by A is the binding energy per nucleon, which is very, very important. So even though, for example, we say GDP, okay, GDP per capita means GDP per person. Okay, so GDP may be very high, but GDP per capita is very small because India is a largely populated country. So this is the GDP per capita. This is the total GDP. Clear? Those who understand finances, nowadays finance is very common amongst you, maybe you are not aware. So let us understand that it is the total marks of all the students combined. Okay, total marks of your exam, all the students combined. This is the average marks per student. This is the average marks per student. Okay, now let's move on to a question. The mass defect of helium 4-2 is 0.03 U. The binding energy per nucleon of helium in MeV. So binding energy per nucleon. So how many nucleons are there in helium? The total number of nucleon is 4. The mass defect is delta M equals to 0.03 U. Okay, now what you have to do, you have to convert it into kilograms, you have to convert it into then convert it back into multiply with c square, then convert it back into MeV. That is a long process. How to solve this? So only one way is that, as I told you, you can convert it directly into energy by multiplying one conversion factor, which is 931.5, or in this case I am using 930. Okay, and in this particular problem even I can use 1000 as well. 930 is very close to 1000. Okay, total number of nucleon is so let me use that only. Okay, because it does not matter, we will, all the values are so much separated, it does not matter. Okay, all the values are super separated, and if you are solving this problem for KCET, you will not be allowed to use any calculator. So let us use the conversion factor as 1000. So U to MeV. Okay, 1U 930 MeV. For some practical purposes that can be taken as 1000 as well. Okay, so this is the total binding energy. Okay, that is 30 MeV. This is the total binding energy. That now this is not the over. What you have to do, you have to binding energy per nucleon. Binding energy per nucleon is 30 divided by 4. So that will be 7.5, approximately 7.5, but it will be slightly less than 7.5. So which one is our answer? Now you can see that 7.5 is our answer. Only one value is closer to 7.5, which is 6.9. Now why there is a difference? Because we have increased the value of 930 to 1000. So that means our value increased a lot, and that's why our answer should be slightly more than whatever we are getting. Okay, so this is the correct answer, 6.9. If you use 930 and wasted 5 minutes of your time, you would have got 6.9. But if you take 1000, you will not waste any time. Within just 1 minute, you will be able to solve the question. So these are the tricks and tips to solve any tricky question. Now let's move on to nuclear binding energy. Binding energy per nucleons versus mass number graph. So this is the graph. If you see this graph, the graph starts at the smaller value. It goes up, then there are few spikes, and it almost becomes flat, and then it goes down. Okay, it becomes highest. The binding energy per nucleons become highest for this element, which is iron. Okay, iron has the highest binding energy per nucleon. This is the most stable nucleus. Okay, so iron is the most stable nucleus because its binding energy per nucleon is highest. So there is an objective question: which of the following is most stable? Which of the nuclei is most stable? Iron is most stable. Okay, remember that. Feature of this graph: the binding energy per nucleon EBN is practically constant, that is independent of the atomic number for middle region of the graph. EBN is lower for both light nuclei and heavy nuclei. So both, as mass number increases, EBN decreases. Okay, a very heavy nucleus, say A equals to 240, has lower binding energy compared to that of the nucleus with A equals to 120. Thus, if a nucleus of 240 breaks into two 120 nucleus, the nucleons get more tightly bound. That means it is more stable. Okay, and extra energy is given out in the process. This is known as nuclear fission. Fission means breaking apart. So higher value of atomic mass number, they have a very low amount of binding energy per nucleons, and they try to gain higher binding energy per nucleon, and that's why they break apart. And once they break apart, the extra energy that is associated with this system, that releases, and you get the atomic energy. This is the atomic energy, nuclear fission. Consider two very light nuclei, A less than 10, joining to form a heavy nucleus. The binding energy fused heavier nuclei is more than that of EBN of the lighter nuclei. This means that the final system is more tightly bound than initial system. This process is known as fusion. This is the common process of fusion. Fusion means combining two, fission means breaking two. Okay, breaking bad. To bind a nucleus together, there must be a strong attractive force of a totally different kind. This force is known as nuclear force. The nuclear force is strongest force in nature. The nuclear force between neutron, proton, and proton are constant. Okay, nuclear force is independent of charge. The nuclear force between two nucleons falls rapidly to zero as their distance is more than a few femtometers, 1.2 femtometers. Okay, this leads to the saturation of forces. That is, the force is constant within certain region. Okay, medium of large size nucleus, which is the reason that constancy of the binding energy per nucleons. Okay, so if you see this graph, you will see that initially if they are very close, if the nucleons are very close to each other at this point, okay, this region where Coulomb force is very, very strong, because Coulomb force is inversely square proportional. So at this case, you can say the distance is almost zero. So if the distance is almost zero, then the nuclear force is very, the repulsive force is very, very strong. But as they are going in, okay, suddenly after some point, the around 0.8 femtometer, okay, the nuclear force starts dominating. So up to 0.8 femtometer, 0 to 0.8, Coulomb force dominates. Obviously, Coulomb force is inversely proportional to the distance. So distance small means Coulomb force can be infinity. So that means nucleons cannot stay closer to this value. So if nucleons are closer than this value, they will be repelled. but when they are moving out of this zone, there is suddenly the potential energy becomes negative. Potential energy negative means it is stable. It is stable. Okay, and around this zone, okay, so this is I think 0.6. Let me remember, this is 0.6, this is around 0.8, okay, and this around 2.7. okay, so nuclear force dominates in this region at 0.8 femtometer. Nuclear force is very, very strong, and it is attractive in nature, and it binds the nucleons together. So it is not allowing the nucleons to go too close, or it is not allowing the nucleons to go too far as well. So every nucleon in this region, they are tightly bound with the nucleus. Okay, so nuclear force is a different type of force, not like our electrostatic or gravitational or frictional force. It is a completely different types of force, and that's why it is considered to be one of the fundamental forces in nature. This is the strongest force, okay, because it can, at this zone also, Coulomb force is very high. Okay, Coulomb force is very high even in this region, but nuclear force can overcome that high amount of force, which is actually dependent on distance. Coulomb force dependent on distance, nuclear force is almost independent of distance. It only works in a certain zone. During that zone, it is almost constant. Okay, now there is a property of nucleons, that is called radioactivity. The detailed radioactivity is deleted. Only few concepts that you need to remember. Radioactivity was a nuclear phenomenon in which an unstable nucleus undergoes a decay. This is referred to as radioactive decay. So to gain stability, a nucleus decays into smaller particles, give away something out, give something away, right? And that is called radioactivity. Now three types of decays are possible. Alpha decay, in which helium nucleus is emitted. For example, the bismuth 83214, right, in alpha scattering experiment, that basically a source of alpha decay. Beta decay, in which electrons and positrons are emitted. Positrons are positively charged electrons. Mass is same as electrons, but charge is same as proton. Gamma decay, in which high energy, hundreds of MeV or keV, okay, photons are emitted. So this is a gamma decay. Gamma decay is energy only. Beta decay, electron. Beta particles are electrons. Alpha particles are highly charged, highly energized helium. Okay, now fission and fusion, as I mentioned, when a heavy nucleus is bombarded with other nuclear particles such as proton, neutron and alpha particles, etc., it breaks into two smaller stable nucleus called daughter nucleus. So this is the daughter nucleus, and you are getting this process is called nuclear fission. The fragment produce star radioactive nuclei. They emit alpha particle, beta particle, they emit beta particle, okay, in succession to achieve a stable products. The source of energy in nuclear reactors, which is produce electricity, is nuclear fission. The enormous energy released in atomic bomb is also nuclear fission. So nuclear power plants and atomic bombs, they all are making from same process, that is nuclear fission. So you can make nuclear power plant which can run a country, or you can make a nuclear bomb which can destroy a country using the same property. Okay, now nuclear fusion. Fusion is the process where lighter molecules, lighter elements merge into form a higher element. Okay, when two light nuclei fuse to form a larger nucleus, energy is released since the larger nucleus is more tightly bound. This is one of the example. And in stars, for example our sun, the same process is happening. Here 4 hydrogen is fused to form helium and energy. Okay, so this energy is actually what is keeping us warm. Okay, because of this process is happening continuously in the sun, and during that process it is emitting a lot of energy. That energy is coming towards that in the form of radiation, heat and light, and that is keeping us warm. Okay, so the energy, all the stars, the blinking light that you see in the sky, is basically result of this. Okay, so all the stars actually produce energy in the process of fusion. So the source of energy in stars is nuclear fusion. Okay, this is the end of this lecture. So if you want to become a star and if you want to download the PDF of this lecture, definitely go on to the link given in the description section of this video to download this PDF. I'll be back with a new lecture very soon. Till then, bye.